Hey, what's up? How's everybody doing? I hope you guys are doing all right. And yeah, coming at you live from Maysville, Kentucky. Um, can't help it. Um, Remember that little page that we were working on yesterday? Page 8. Remember how we drew a line in the middle of the page? Yep, we're going to use that space on the bottom of that page, and we're going to be doing us some stuff. What I had in mind to do for this, which we may do still, is I was going to introduce you guys to what I call the station labs, and there's 8 different activities. You can either get up and go to the table where that thing is, or you can take the cards and pass them around and stay where you are. But the whole idea is you guys need to be spread out a little bit, and it usually involves one video that I would put in on one computer and then use the laptop. So those get really cool. And they reinforce a lot of really good stuff. So I was going to introduce that with this subject, and I've already got the papers printed for it, so we may just do it when I get back. But I wanted to at least touch on this stuff, bring it back to mind again as a little intro before we actually did the station lab on the subject. Right? You follow me? So in this stuff you guys have heard before, I'm sure Mr. Davis has taught you this over the years. Very, very confident. We're going to talk about 3 ways that energy gets transferred. You can probably think of them right now. Yep. All right. So here's what we're going to do with the sheet of paper, and I hope this wakes. Yes, it waked. It waked. All right. So here's our line, right, that we did yesterday in the middle of the sheet. And if somebody was absent yesterday, just show them what we're doing. Remember, we're numbering page 8, and then you can put that line right in the middle of it. And then if you were absent, you can just, write down what is above that line. Take a picture with your Chromebook or copy it over when we get done. All right, because I'm going to give you guys some time. There will be some time at the end of class if you need to do that. All right, so beneath that line, what y'all need to write is this right here, energy transfer. That's the 3 ways that energy gets transferred. So this is where it gets a little simple, but at the same time it can get a little complicated, because think of a pool table. How does energy get transferred from your initial lineup, right, and you hit the cue ball? How does energy get transferred to all the other ones? No, I mean really. And does it just get transferred into 9 other balls, or are there particles involved? And what are they doing? Remember, this whole unit really kind of behind the scenes is really all about particle motion, right? We had the kinetic molecular theory yesterday. So watch what happens here. Now, there's a way I want you guys to set this up, and I'm going to do it kind of step by step. We're going to make a great big box in the rest of this page, so it goes like this, okay? And you can take that line all the way down the bottom of the sheet, okay? I'll just go ahead and make that box. Doesn't have to be straight, don't have to be pretty, but those of you that get real, like, it has to be just right. I get it. You can use, what you can do? You could, I've done this in the past, go to the back of your notebook and rip out the last sheet, and then fold that in half, fold it hamburger like we've done, and now you have a straight edge. That's a cheap way of doing it. Do not throw it in my classroom. When you get done, politely throw it away in the trash can. So let's not have that. Okay, but that's a way you can come up with a straight edge. And if you need to do that, okay, I'll give you a few minutes or give you a few seconds rather, to mark that out. Okay. And what you find out is how you draw the straightest line. Don't try to draw a straight line. Don't get so focused on drawing a straight line that you don't just let your hand glide and make the line. It's crazy. When we used to do hand drawings in architecture, I was like, how do you draw it so straight? And one of the guys said, I don't try. I mean, really, you just kind of just take it across and don't worry. It was like, oh my gosh, I have to get it right within that stop. You know. Anyway, just a thought. Okay, now we're gonna put a box at the top. Really, it's gonna equate to a line going across the top like that. And then we're gonna make three little boxes on top. Now make sure that they're big enough that you can write in. You don't have to make them two or three spaces like I did. Just make sure it's big enough you can write in, because we're going to write 1, 2, 3. Uno, dos, tres. 3 words. 1 word in each of the boxes. Okay? And we'll deal with it one at a time. And I'm not suggesting as I go through this that the way that I describe it, the way that my definition, that you have to write it word for word. Remember, never. Not really. You can certainly paraphrase it in a way that makes sense to you. By all means. Yeah. So what we're going to do is, like I said, 1 word is going to go in each one of those boxes. And then below that, we're going to kind of write a definition-ish. Toward the bottom of the great big box, we're going to write down some examples that we might be able to, and you guys could think of too. And if you guys think of examples that is not on here, put them in there. Yeah, I mean, if you have room. Sure, why not? Okay, so the first means of energy transfer is conduction. So let me talk you through it, and then we'll actually throw out the definition, right? Conduction. One of my mentors was a radio guy that worked in the FBI down in the basement. Mark. You'll hear a lot of stories about Mark. But he got in the FBI and with Dad, not at a different time. But he got transferred to Cincinnati, had no place to stay. He was staying down along Route 50 on Columbia Parkway in Cincinnati at El Rancho Rankin. Ugh. I mean, it was a flea bag motel is what it was. And so Dad found out about it, moved him in, and all of a sudden, hey, I got a big brother. Well, he was into radios and electronics and all this kind of stuff. So we would use little 9-volt batteries and their little snap things off of stuff. I'd be cutting them out of old walkie-talkies that didn't work and making up lights that blink and all that kind of stuff. It's nothing more annoying when you get everything together and flip the switch and nothing happens. There's no conduction. You forgot to connect a wire. Wire is one great example. All the electricity in your house. Damien, that I mentioned yesterday, he's hooking up, electrical stuff. And we talked about that. The making sure that every connection is sound is the way that it ought to be. That's one thing. I've also talked about heating up noodles. So now think about, if I'm heating up spaghetti noodles, where is there conduction in that event? Conduction. Remember, just like wires had to be touching. So where's the conduction when I'm trying to heat up spaghetti noodles? One thing about this stove, don't tell anybody. One thing about this stove, it was in the house, but some of the burners, they're not perfectly level. They kind of go like that. That's really annoying. The 2 smaller ones, yes. 2 smaller ones are fine. The bigger ones, I don't know what they put on this thing, but they're kind of so never ran into that before. So sometimes I have a hard time with the conduction. Yeah. So as long as my pot of water is touching the coils, there's a conduction right there, right? There's contact. There's physical contact. Here's another one. Now, I don't know how you guys are about, I haven't seen much of it, but I don't know how you guys are about there's a little sweetie at school and I like her, and I may have seen this a lot more in a bigger population, but, and I want to go to class. I want to walk her to class, and I'm always tardy because I have to walk her to class and then walk back. You better get your tail in my classroom before that bell rings. Now, but I'm going to tell you, that got too many people. And I'd have to holler at people that I really didn't want to have to holler at because they wanted to walk their girlfriend hand in hand, right? Oh. Honestly, when you're holding hands with somebody, you know, there's conduction there. You can feel that. Boy, can you feel the heat? No, you know what I mean. You can feel the heat. He's like, stop it, you guys. Um, yeah, you can feel the heat. Yeah, grandmother touches on your face. It's, oh, look, it's the heat just growing so big. Yeah, you feel the heat from it because there's contact, there's conduction. Sure. And you guys could probably think of a lot of other examples. Anytime you've this past summer, right? You get out of the car and don't, without thinking, you put your hand down on the car and you're like, maybe not, right? There's conduction there. Your hand's touching the car. So a lot of examples in everyday life, but there we go. So let's write this down and see. Energy transferred by objects being in direct contact. Now, when they are in direct contact, watch this. Here's the object where the object, here's the object. Hang on, I'll get it right in a minute. Here's the object where the particles are moving faster, so we have more thermal energy, and it comes into contact with something that doesn't have the particles moving very fast. Now here's what I want you guys to really think about. I'm not, no kidding around. Here, I'll do the hot object a little bigger. I'll just take my finger and stick it up. Okay, this is the hotter one. And they come in contact. So what does this energy, the amount of energy in this, do to these particles? That's the real question here. It causes them to move faster. All of them at one time? No, it warms up. Same effect, y'all, as when you put ice in a glass at room temperature. Or even bring the ice, no, we're getting deep here. Bring the ice out into a room at room temperature. Where's the contact there? Where's the energy coming from? That's right, the particles in the air. You got it. Yes. I've talked about how the winters, the temperature. If you weren't in the room when I mentioned this, let's think 45 degrees up here. I mean where we are. 45 degrees. Think of the kind of clothing that you'd wear at 45 degrees. Not too much, right? Maybe a hoodie, right? The difference is, y'all, is that the amount of air, the amount of water particles in the air up here. Water particles in the air up here in December is way less than the amount of water particles in the air in Florida same time of the year. Yeah, because it's a peninsula, y'all. I mean, you got water evaporating on both sides of them. So, and what happens is that water in the air gets to be about 45 degrees and it makes contact with your skin, your face, your arms, right? And it bites more because you're surrounded by these water particles that are just sucking the thermal energy right out of your skin. And it's different. Believe me, you want to wear a coat, a hoodie, and anything you can to keep you from getting exposed. Not necessarily at 45 degrees, but you get around 40, 35, you know it. Yeah, you know it. You do not want to go out in shorts in 40 some degree weather. You will get very, very cold. That heat loss is nuts. Conduction. It all has to do with conduction. You think I'm telling you a story about Florida. It's about conduction. The water vapors just pulling that stuff out of your skin. Okay, so all these examples that I gave, what we're going to do here is we're going to write some examples down below this definition. And we'll do this for all three. Okay, so here's a few that I recall that I brought up. Wires, right? A pan on a stove, your hands. You could put water vapor in the atmosphere. I mean, now you know the significance of that when it's cold. And see, it works the opposite up here. less water vapor in the air. Okay, and you walk outside, you don't even need a hoodie, man. You just throw on a coat and you're like, yeah, I'm good. 40 degrees, big deal. Yeah, because you don't have a whole lot of things pulling that thermal energy out of you. Yeah. So, a couple more could go down there. All right, this next one gets really cool because you actually see this a lot more than you think you do. This next one is convection. And it really comes into play when you start looking at how energy moves through the planet. One of the big things that I want to point out is on the surface of the planet, doesn't air, correct me if I'm wrong, I think I'm right, doesn't air closer to the ground get heated up by the sun? Well, sure. Yeah. And that heating happens more often because gravity's pulling on all that air, right? Those air particles, and holding it closer to the surface. And because it's doing that, it's got them concentrated. Air pressure's greater down here, where we are, right? Well, as those air particles get heated up, here's the thing. No matter where you are on the planet, as the air particles heat up, they spread out, right? They don't concentrate. That goes against everything we learn in solids, liquids, and gases. They spread out. And when they spread out, they get hot and they rise. Now, for us to imagine airflow, here's the surface of the planet. Airflow going this way and this way, that's easy, right? And you say, well, that's because of the weather. Yeah, but what's causing this chunk of air over here to slide in? I thought there was air that was here already. It was here, and then it got heated up, and it went straight up into the atmosphere. It vacated. You got a chunk here where it vacated, and so surrounding air moves in. That's why, guys, you end up with a lot of fierce wind and different weather events, let's put it that way, where there's a lot of up swoosh. That's not even a weather term, but you get the idea. Things get heated up, the air goes up, we don't feel it, but then it comes in horizontally. That's when we feel it. Little breeze going on. Hey, boy, that feels good, especially when there's a big change throughout the day of, is the sun there or not? Right? Because when the sun's there, it's like constant. But let it start to go down or let it first come up, and there's a little bit more breeze happening. There's convection. A real simple one is that illustration that we did at the end of solids, liquids, and gases. A hot air balloon. Heat the particles, they go up. They get up here, the heat goes out of the balloon, and the particles kind of settle down, and so it sinks. Right? I have to find them. If you take, when you do a 3-hole punch and you got the little roundy things, I think they call them Chads. Sorry, Chad. But if you put them in a mason jar and fill out their jar with water and heat it up, you can actually see this motion going on with the Chads. I mentioned that to you guys when I talked about heating the noodles, that they started rolling in the pan of water, that I never really had paid attention to that. And literally the motion of the noodles was this. Remember, they weren't just laying here getting, going from straight to not straight. I actually saw them rolling in there, and that's what told me these things are probably ready, because they're flexible enough that they can actually kind of roll like this. And that was convection. It was hot water's going up, the heat's dissipating, and then the water sinking back down. Happens in the ocean too. Creates deep ocean currents. And that's a whole nother cat that we could deal with, but the deep ocean currents cause exactly the same way. Water is heated, at the surface, obviously, and then it's kind of a combo between weather and chemistry, but there's this upwelling, and that's what they call it, upwelling in the ocean of water circulating. Cool air being forced up as hot air is forced down. So it's just this constant cycle that happens. Here's the deep water, it goes this way, and it is like that. Alrighty, so here's the definition. Visually, we can kind of know what it looks like. Here's the definition. Energy transferred by objects rising from heat, then cooling, and then sinking. And you may want to put period, and the whole thing happens all over again. Right? Just like my water when I was trying to heat the noodles. Yep. And so a lot of different examples that we could bring out. And I mean, I wish we could spend a lot more time on this because, and I wish I could hear you guys give me some good examples because I know you guys are thinking of some. So we've got the balloon, got the atmosphere, ovens. It happens this way in your ovens. Yes, it do. If you have a convection oven, hey, what's up? You know what that means now. Yeah, think of where the burners are. The burners are on the bottom, aren't they? Unless you turn it on broil and then it heats the one on the top, but that's different. It's doing something different that we're going to deal with here in a second. But most of the time, it heats the ones on the bottom, and the heat goes up, hits the inside lid, and it's forced back down. So there is this motion. I'll do it real slow so you can see it. There's this rising, hits the lid, and it circulates back up. And that's how your oven heats stuff. That's why the bottom tends to cook more before the top does. Oh, see, you accidentally learned something today in class. Daggone it. That always happens. Ocean currents, too. So you write, and I'm going to get a drink. Well, I got one of them cough drops in my mouth so I can teach y'all. Oh, learn you some science. Very freaky. All right, here's the last one, and this one gets kind of cool. And you've learned about this, and it is so much around you, especially when we get into one other example. This one's everywhere, man. It is everywhere, and that was radiation. I wonder if I can move me. Nah, where I'm at. I don't think I can. Oh no, I can't. Okay, that's energy transferred by being emitted out from an energy source, right? So I've got an energy source. Let's just be real obvious about it. There's a great big energy source about 3 planets over from us in our solar system. What's that big thing called? The sun. Yeah. They are saying it out loud, aren't they? They're supposed to be. This is my classroom. We do things like that. Yeah, the sun, sure, radiates out the energy. In my astronomy class, that's what we were talking about before COVID slapped me. And but yeah, radiates that out in all directions. Now that's the crazy thing. The energy's not just going towards Earth. It's going from the top, the bottom, the side, the left, and down and under there, down its leg, up off its shoulder, out of its ear. Or it doesn't have any ears, does it? I mean, literally, but it's going everywhere. And there's things that happen on the surface of the sun that we don't even know about because, like, this is going to be hard to do. But, like, here's the sun, and then here's us, and then something happens on this side of the sun, and it goes that way, and we never know it. It's going out everywhere. Remember when I showed you gas, click, plasma, click, gas, click, plasma? It's happening right above your heads right now. Yeah, radiation. It's light. Light's coming from those gas tubes above you. You are radiating heat right now. And now we're going to get really funky. Did you know that every human being emits, and the exact frequency varies just a little bit, just a pinch. The human body actually radiates electromagnetic waves at a very specific frequency. Now we could have some real fun with that. but it's by video, and I can't see your faces, and I can't see you go like, what? Like that, which was really good, because I know Ryan would be doing that. I mean, and well, even Luke would be like, you know, I mean, he would be like, I don't even know what the man just said. And Traven, forget it. I mean, he just would be like, Huda, you know. Yeah, but you guys, every single one of you emit a certain frequency. Have you ever noticed, let me put it this way. Have you ever noticed, you see somebody at school, and from what you see, you like, and whether, let's just keep it friends, right? You think, it's like, I think I would like that person, and I would enjoy myself being in their company. And you get in their company, and it's just, your frequencies aren't matching up. Mm-mm. And it doesn't matter. You don't have to be the same size, same height, nothing. But you get around some people, and it's just harmony. Could be that your specific frequencies are riding together in this beautiful wave. Could be. I'm going to throw another one out to you. Have you ever had someone come up behind you and put their hand on your shoulder or whatever? I mean, in a nice way. And you knew immediately who it was? Because you know that person's frequency. Are we starting to explain some Sunday morning things? We could be, but I'd rather us wait till I get back. So, yes. Some matters supposedly not in science that probably are. Yep. Mason, you got that? You got that? Energy is being radiated out. So there's all kinds. Chloe and Robert, you are writing this down, Robert? Thank you. Okay. You're good. Thank you. And Monty, make sure Izzy's writing this down. Thank you for your help yesterday, Izzy. I appreciate that. All right. So, all kinds of examples, y'all, and then we're going to just be done. I don't know how to move me. I'd like to move this picture.